Imagine a silicon chip the size of your ID picture. You can place it right on your skin, put a droplet of fluid, zap it with an electric pulse, and there you go. Your cells get transformed into something else, a follicular cell, an endothelial cell, a neuron, whatever kind of cell you want. Now, this approach was actualized by the Ohio State University's Wexner Medical Center and College of Engineering last August. It is known as tissue nanotransfection, or TNT. By applying a focused electrical field through array nanochannels in the chip, you benignly nanopore the juxtaposing cell membranes and electrophoretically drive reprogramming factors into the cells. These reprogramming factors, of course, differs depending on the desired outcome. For example, if the researchers want to convert the skin cells to nerve cells, they use a different code than they would use to convert the skin cells to bone cells. You can go as far as repairing and regenerating the stroma, the tissue that serves as the framework for your organs. Essentially, this approach takes advantage of the fact that the skin is a fertile medium to grow these cells. What's good here is that you have something that is efficient and non-invasive. As compared to the different cellular therapies right now, TNT doesn't require any laboratory-based procedures and may be implemented at the point of care. Plus, it is not as stochastic in nature. Diagrams A and B demonstrate that they were able to reprogram the fibroblasts into induced neurons. This is for a mouse with a middle cerebral occlusion stroke. Meanwhile, diagram C shows that they were able to change the skin cells to endothelial cells that form blood vessels. Within a week of treatment, the mouse had blood flowing through its leg again. Not only did the process work to reprogram local cells at the site of the injury, but the entire leg was affected. This is because the mouse's body also did some work to repair itself. This is interesting because there are steps that the body itself mounts for its own rescue, so they're somehow enabling the body's rescue system by tipping it off. If you're going to think about it, the concept really is simple. Cellular therapy and cell reprogramming has been around for quite some time. It was just delivered differently this time around because they used a nanochip. And nanochips have also been around for more than a decade, although the nanochips were usually developed for diagnostics. It was used like a gel electrophoresis setup where biological components are separated in the chip to detect alterations in the DNA. So in a way, it is a hybrid of technologies. However, there is no patent for this breakthrough yet. The closest thing we have to it is IBM's lab on a chip. They are still exploring the diagnostics application, but they already have a pending design patent for the microfluidic device. TNT-based tissue reprogramming has the potential to ultimately enable the use of a patient's own tissue as a bioreactor to produce autologous cells that can resolve conditions locally or distally upon harvesting. This simple to implement TNT approach, which elicits and propagates powerfully favorable biological responses through a topical one-time treatment that only lasts seconds, could also find applications beyond plasmid DNA-based reprogramming strategies, including oligoRNA, mediated reprogramming, gene modulation, editing, and so on. Perhaps it can be even combined with CRISPR-Cas9, the genome editing tool that has been recently creating a buzz in the science world.